Hello everyone. Welcome back to Swecodes. Welcome to our deep dive into Leetcode problem number 2392. Build a matrix with conditions. This challenging problem combines graph theory and matrix manipulation, offering a great opportunity to sharpen your algorithmic skills. Let's start by understanding what we're dealing with. We're given a positive integer k and two 2D integer arrays, row conditions and col conditions. Our task? To build a k by k matrix containing the numbers 1 to k exactly once, while satisfying all the given row and column conditions. Sounds tricky, right? Don't worry, we'll break it down step by step. Before we dive into solving, let's quickly go over the constraints. The matrix size k can be anywhere from 2 to 400. Both row conditions and col conditions can have between 1 and 10,000 elements. All values in these conditions are between 1 and k, and each above value is different from its below value. Same goes for left and right. These constraints will guide our approach to an efficient solution. Let's look at our first example to get a better grasp. We have k equals 3, row conditions equals 1, 2, 3, 2, and col conditions equals 2, 1, 3, 2. The output matrix satisfies all conditions. 1 is above 2, 3 is above 2, 2 is left of 1, and 3 is left of 2. This example shows us how the conditions translate into matrix positions. Now, for our second example, we have a case where it's impossible to satisfy all conditions. With k equals 3 and conflicting conditions like 3 must be both below and above 1, we return an empty matrix. This example highlights the importance of checking for contradictions in our conditions. So, how do we approach this problem? Our initial thoughts lead us to represent these conditions as a directed graph. We'll need to check for cycles, as their presence would make a solution impossible. Then, we can use topological sorting for both row and column conditions. Finally, we'll build our matrix based on these sorted orders, being mindful of incomplete condition sets. Our optimal solution follows these steps. First, we create adjacency lists for row and column conditions. Then, we perform topological sort using Kahn's algorithm. If this fails, we know there's no valid solution. If it succeeds, we create our k by k matrix and fill it based on the sorted orders. Let's see how this translates into code. Now, let's walk through the Java implementation. We start by building graphs for row and column conditions. Then, we perform topological sort on both graphs. If either sort fails due to a cycle, we return an empty matrix. Otherwise, we create our k by k matrix and fill it based on the topological orders. The buildGraph function creates our adjacency lists, while topological sort implements Kahn's algorithm. This algorithm is crucial as it detects cycles and provides us with a valid ordering if one exists. Pay special attention to how we handle the matrix creation. We use the results of our topological sorts to determine the exact position of each number in the matrix, ensuring all conditions are met. Let's break down the time and space complexity of our solution. Time-wise, we're looking at O, n plus m plus k, where n and m are the number of row and column conditions respectively. This accounts for graph construction, topological sorting, and matrix filling. Space-wise, our overall complexity is O k squared, mainly due to the k by k matrix we're creating. We also use O, k plus n plus m, space for graph storage. Imagine you're a city planner tasked with arranging buildings in a grid-like city, but with specific rules about which buildings should be above, below, to the left, or to the right of others. This is essentially what our code is doing, but with numbers instead of buildings. We're given a size k for our city or matrix, and two sets of rules. One for rows, above or below, and one for columns, left or right. Our job is to place the numbers 1 to k in a k by k grid, following all these rules. Our solution tackles this problem in 4 main steps. Building the graphs. First, we create 2 maps of our rules, one for rows and one for columns. These maps are actually graphs where each number is a point on the map, and the rules are like one-way streets between these points. Sorting the graphs. Next, we use a special technique called topological sorting on both of our maps. This is like finding a route through our city that follows all the one-way streets without getting stuck in a loop. Checking for impossibilities. If our sorting step finds a loop, like A must be above B above C, and C above A. We know it's impossible to arrange our city, so we give up and return an empty map. Building the city that is the matrix. If we successfully found routes through both our row and column maps, we use these routes to place each number in the grid. We create our graphs using lists. Each number has its own list of neighbors, the numbers that should come after it in the arrangement. Topological sorting is the trickiest part. We use an algorithm called Kahn's algorithm. We start with buildings that don't have any buildings that need to be before them. We place these buildings, then look at what buildings can now be placed because all the buildings that needed to be before them have been placed. We keep doing this until we've placed all buildings or we get stuck. If our sorting algorithm can't place all the buildings, we know we have an impossible situation, a cycle in our graph. So we return an empty matrix. If we successfully sorted both our row and column rules, we use these sorted orders to place each number in the grid. We do this by figuring out what row and column each number should be in based on our sorted orders, placing each number in its correct spot in the grid. This solution is clever because it transforms a complex 2D problem, arranging numbers in a grid, into two simpler 1D problems, arranging numbers in a line for rows and columns. By solving these simpler problems and then combining the results, we can efficiently solve the original complex problem. It's like planning a city by first deciding the order of buildings from north to south, then from east to west, and finally using these two plans to place each building in its exact spot in the city grid. And there you have it. We've solved the build a matrix with conditions problem. Remember, the key to cracking this problem lies in effectively using graph algorithms. Keep practicing and you'll master these techniques in no time. Thanks for watching, and happy coding!